Okay, hello everyone. So the next section we are going to cover is section 8.3. This is about the geodesics of the light rays. This and the next section are covered somewhat superficially in the book, so that's how I'm going to cover them, and I will probably just merge the videos after shooting them. Now, so far we have looked at the particles with finite mass, but of course we're also interested in particles that do not have a finite mass and move at the speed of light. So these will be photons and gravitons and perhaps other exotic particles. Now, the problem with those particles, so I'm going to refer to them as photons from this point on. So, but when I say photons, just think of particles with zero mass and that move at the speed of light. So for the photons, what the fellow geodesics, the so-called null geodesics. So for any kind of motion they do in any kind of space-time, the distance they cover is always going to be zero, right? So if this is zero, then the proper time, as we defined this way, is also going to be zero. So if this is zero, then how would you calculate this integral, right? So how would you go from point A to point B, calculate this integral, and try to use a variational principle, right, to try to find an extreme value? It just is not going to work. Now, what this tells you is that the proper time is not a good parameter to parameterize the world line of photons, right? So, but you can, of course, choose another parameter, and using that parameter, we can define some tangent vector. So let's say we have some world line for our photon. It doesn't need to be straight like this, of course, but we are going to choose some parameter to parameterize this, and we can still define a tangent vector and get the for velocity, right? So if our parameter is something like lambda, right, the for vector is going to be just the derivative of our position with respect to this lambda. If this lambda is an affine parameter, remember we defined affine parameters that would have a certain property, and that property is that d square x alpha by d lambda square is equal to 0. Okay. So if it's a affine parameter, we're also going to satisfy this, which is very nice because this looks like the equation for the free test particle in flat space-time, right? It will have no acceleration. This is actually Newton's first law, right? So by the way, if you define your for velocity this way, then the for velocity's dot product by itself, it is some tangent vector. Then let's not call it for velocity, but if this is a tangent vector defined by any parameter, this is always going to be 0. But if it's an affine parameter, we also have this value, which means that we can take this and generalize this. So remember, for the particles with finite mass, we started with something very similar. We started with this, the tau square equals 0. Then we generalized this into having some Christoffel coefficient, the x beta by d tau, the x gamma by d tau. Right? So this is how we generalized this to curved space-time. This was true for particles in flat space-time, and this became that for particles in curved space-time. Right? So we're going to do something very similar. So for the photons, we start with this, and we are going to say that for the photons, the geodesic in curved space-time is still given by this alpha, beta, gamma. The x alpha, the lambda, and the x beta, d lambda. Right. So this is our geodesic equation for photons in curved space-time, and this lambda is some affine parameter. Right? It has to be an affine parameter because we want to have this in flat space-time. So in flat space-time, of course, the Christoffel coefficients vanish, and this really reduces to this. So this really has to be a affine parameter. Now, as far as I can tell, there are no questions at the end of the book that actually uses this, and there is one one problem that I plan to solve about the motion of photons, problem 11, I think, but it's much easier to solve with killing vectors. That's the proper way to solve this, but perhaps I will mention approaching it from this point of view. So the way to use this, so killing vectors are useful when, of course, you have symmetries. Well, killing vectors exist when you have symmetries, so if you don't have symmetries, then you can't use them because they don't exist. But if there are no symmetries, then you write this. You calculate your Christoffel coefficients. I mean, you're talking about photons, and we mentioned how to calculate Christoffel coefficients from the metric when we were discussing particles, but that discussion is valid. It's a property of the space-time. So you calculate them using the equation from the Christoffel coefficients. So let's find my sheet here. So where was it? Yeah, the last one. Right, so this last equation, using the metric, you can calculate your Christoffel coefficients, and then you can get a set of differential equations and try to solve them. But as I said, for many of the cases of interest, it's actually much easier to use the constants of motion and the killing vector. So we are going to be doing that. So this is all I have to say about this topic.